Let's talk about one of the most controversial materials on this planet. Uranium? No. Sugar? Not this time. Let's talk about plastics. We all know the plastics, and we use them every day. We know about the benefits that they have for our daily lives, and also what they can enable related to sustainability. But we also know the pictures that are terrifying us in the news every day about microplastics and plastics getting dropped in the ocean and just lingering in the environment, and also the carbon footprint that is associated with the petrochemical industry and the plastics industry, which is one that is hard to decarbonize. And so I think the solution to this problem is actually in this picture behind me. And I would like to have a little survey here. What does this symbol mean to you? Anyone? Good. Okay, I hear recycling. That's good. In fact, this I would call is a wish cycling symbol. All we do, we go to the recycling bin and we sit there with our, take out food and with all the plastics that we end up with, and we think, is this recyclable? Can I put it in there? And so what we do is we put it in there, but we have really no idea if it is actually recyclable. In fact, it may well not be because it doesn't have a value in the marketplace. The recycler wouldn't get any money for it. So that's a problem. I think much more interesting is the number that nobody knows about. The number tells you about the chemistry. And so the chemistry is really what enables you to really know and understand what's behind the plastic. The plastic has a bunch of polymers in them, and there's a chemical structure that could be PET, polyethylene, PVC, polyurethanes. They're all so different. And this chemical structure is very fascinating and it's useful. The problem is, right now we don't care about that chemistry at all. In our current recycling flow, we really live in a downcycling world. The paradigm right now is we take all the plastics and the other stuff. We put it in the recycling bin and it will be sorted in the different materials. Yes, potentially. But they all go down the exact same mechanical recycling process, which is basically grinding, shredding, and melting the plastic into a new shape. We don't care about the chemistry at all. That only enables us to take a plastic bottle into a textile, a rigid, hard material, into something soft. And then it goes into the landfill because it's not recyclable anymore. Constantly, we're degrading materials as we use and wish cycle them. In the future, I think we can do much better. We can use the plastics and we can actually think about the chemistry again and understand what's in them and what are the building blocks of the plastic and how can we recover them and make them into new plastic. That's a process that enables us to actually take plastic materials with high quality and turn them back into plastics that have high quality and a value in the marketplace. And we can do so over and over again. Now, to understand how this works, let's do a little bit of chemistry. I'm going to walk you right through it. Let's think about the example I had before, PET, one of the most popular plastics on the planet. What does it actually stand for? PET means poly, which is many. We have many, many, many of the same kind. And E and the T's, I won't go deeper into it, but that's the chemistry. That's the E and the T's and the E and the T's strung up together. That makes a long, long polymer chain. And that, for a plastic bottle, needs to be fairly long because those polymer chains, they entangle and they give you the strength that the plastic bottle needs. A textile, on the other hand, is okay with much shorter chains. That's why we can always take a bottle and grind it and lose a few E's and the T's, and then we can make it into a textile. But then nothing again. It's a one-way street at the dead end. With chemical and biochemical recycling, we can do much better. We can take the PET and we can take enzymes genetically modified, we can do catalysts, we can take acids, alcohols, we can take a variety of methods that we and other researchers around the world are working on and take these monomers apart and string them back up to a long, long polymer chain of whatever quality we want. That makes finally a truly circular plastic material, and that's what the market and all the companies right now desperately need. You see here that these recycling processes are not easy, right? Each arrow means that's a process step. So the more process steps you have, typically the more complex and the more energy intense it gets. So something that I find fascinating is that you can also take polymers and you can use something called thermodynamics and take them into a cyclic ring structure. Those rings are also something you can recover, but you don't have to break all those E and T bonds. And so you take the rings and you open them in something called ring opening polymerization, and you string them all together to a long, long polymer chain. That way, you also end up with a virgin grade material, with fewer process steps. Another thing that's very important, of course, is that you can remove the impurities. In the marketplace, all the plastics basically, or many of them, have color and other additives. So in reality, in the lab, looks like this. Basically, a bunch of Breaking Bad style cooking with using some catalyst and sort of a smart way of using temperature, distillation, and pressure. That gives us the virgin grade material when something is recycled chemically. Now, quality of plastic is not the only thing that we need for a circular material. What else is important? Cost and environmental footprint. People will not take any virgin grade, high quality plastic material at any cost, and we should not aim for circular materials at any environmental burden. To understand the cost and the environmental footprint of this process, we do something called techno-economic analysis and life cycle analysis. We really have to compare with the virgin and the traditional fossil-based process, in which typically you have energy demand and carbon footprint associated with the crude oil extraction, the steam cracker, with the monomer production, polymer production. That gives you a carbon footprint, roughly 4 to 5 kilograms of CO2 per kilogram of PET. Now, what we really want to do when we think about recycling processes, ideally we want to cut out most of these energy-intensive processes in the petrochemical industry. And we can do so if we think of it, the plastic manufacturing, as a supply chain, and we really want to only go back a few steps from the plastic and the polymer back to the monomer, but not all the way back to the fuel. That would create a much larger carbon footprint. In our case, we can cut the energy demand and the carbon footprint by 80%. And we don't stop there. There's a process that is low in energy intensity, so it's something that can be easily decarbonized, much easier than the petrochemical industry. So this is the process that the industry needs right now, because the big brands are putting pledges out. Everybody wants to use a certain recycled content. But these pledges will have to be missed if we rely on mechanical recycling alone. We need upcycling and chemical and advanced recycling methods to come online right now. Only with those we can make those pledges, and we can have a future where we can use 100% recycled plastic. So with this, I'm tremendously excited. This is the process that can enable us to move from a linear economy to a circular economy, where we don't have waste anymore, because any waste material becomes a resource for something else. With this process, we don't have to hate our plastics anymore. We can start loving them again. We can start loving our upcycled, low carbon energy intensity, sustainable plastics again. Thank you.